recording, and let me start explaining these. Okay. I mean, this is just a reminder, right? We have talked about these reference frames yesterday. I mean, I have given the definitions earlier, but now I just started discussing these. So inertial reference frames are the ones that you should use, right? Because all of the laws of physics are, without an exception, they are always expressed in inertial reference frames. So we are always assuming that we are using inertial reference frames. So as a result, some of these laws are not valid in accelerated non-inertial reference frames, okay? So just keep this in mind. So as a result, for non-inertial reference frames, don't use them, okay? That's the most important advice. But sometimes, I mean, for some purposes, you may want to use them. And if you know what you are doing, then provided that you know what you are doing, then it's okay to use them. If you know what you're doing, okay? At least for the laws of mechanics, what we do is, like when we use an accelerated reference frame, all you have to do is to add some kind of a fictitious force. And then I have said that this fictitious force is actually can be considered by adding a fictitious gravity, okay? So that's basically the fictitious gravity is equal to the negative of the acceleration of the reference frame, okay? And I have solved problems with these, okay? So in any case, so today I'm just going to solve some examples using this prescription, okay? In some cases, if I can solve the problem in an inertial reference frame, then I'm also going to do that, just to compare these two approaches, because sometimes it is not necessary to use an accelerated reference frame. Solution of the problem is also easy in the inertial reference frame as well, but sometimes it isn't, okay? So you may want to actually compare these. All right, that's just an example. Okay, I cannot see the whole problem in my screen, but in any case, so we have a situation in here where, well, this is like an elevator problem. I said ceiling in here, but it might be the ceiling of an elevator, perhaps, right? It doesn't matter what it is, all right? So what happens is that the ceiling is accelerating upward. It's just an artificial problem. It's just a problem which is devised to illustrate the methods that we are going to use in here, right? So it's not something from real life in a way. So I'll talk about things from real life. Okay, so it is accelerating up with this acceleration. And well, we have this usual arrangement in here. So we would like to find accelerations of both objects. So let's just assume that they are accelerating upward. So I think I'm going to use this. So let's call this acceleration of this one as A1 and acceleration of this one as A2. And we are going to find these accelerations, okay? I mean, one of them might be negative, but I don't care about this, okay? I will also find the tensions in there. In any case, so this is also a problem which can be solved as easily in an inertial reference frame. But let me just compare these two approaches, okay? So let's say it like this. So there are these two approaches. So in an inertial reference frame, there's a problem. And in the let's say non-inertial frame of the ceiling. Okay, so in this frame, well, that's an accelerated frame. In this frame, let me draw this. Okay, M1, M2. So masses are 2 kilograms and 3 kilograms, right? In this frame, the ceiling is at rest. And the pulley is at rest. Okay, in this frame, it looks like that. There is a gravity in here. So let me call this as gravity in here. G. So that's the real gravity. Let me shift this here. So that's 10 meters per second squared. In addition to that, so let me say plus, there is actually an fictitious gravity. Okay, so just keep in mind that as a vector, this is opposite to the acceleration of the reference frame. So as a result, it must be pointing down. So I'm using this down arrow for that purpose to show its direction. So the magnitude of that fictitious gravity along that direction is 5 meters per second squared. Okay, just keep in mind that this vector in here is anti-parallel to the acceleration of my reference frame. Okay, so in any case, so as a result, the sum of these two, therefore, the sum of these two is basically, I'm just going to call this as the total acceleration. So it's the total gravity in that case. Total gravitational acceleration is 15 meters per second squared. Okay, so from that point of view, therefore, this is a problem which is quite similar to the problem that we have solved before. It has been solved before by using the value of the gravity at Earth. We have solved this before, so I'm going to use the same solution essentially, but this time I'm going to use a different value of gravity in here. And then what else? So I'm going to do, well, what I'm going to do in here, what I will obtain in here is not the accelerations. Yeah, let me use this funny color. So I'll be basically obtaining the acceleration of each of these objects relative to the ceiling, okay? For this one as well. All right, so as a result, let me not use an arrow in here, but in any case, so this is basically a relative acceleration. So as a result, I have to go back to the original frame. So as a result, I have to do this transformation in here. But in any case, let me go back and describe what happens in an inertia reference frame. So in the case of inertia reference frame, things are okay, I believe. Okay, so, well, basically pulley accelerates. So there's an acceleration of the pulley. So I'm going to call this as AP in the upward direction. Let's see, for the ceiling also accelerates. All right, whatever, I mean, we already know this. So in that case, the problem is this, basically obtaining the constraint relationship between the acceleration. So I know that these two accelerations are somewhat related with each other because they are connected with a string. So let's say it like this. Let me also add this gravity in here. So that's the only gravity in here. So there is a constraint relation between A1 and A2. Okay. In this frame too, there is a constraint relationship, but it is easy to express. So we will say that if this block accelerates upward with an acceleration A, then this block accelerates downward with an acceleration A. So it's quite easy to see what the constraint relationship in here is. It is harder in here, right? Let's say it like that, therefore. So the difficulty in here, the main difficulty is expressing the constraint relation. Okay. In that case, for this case, the difficulty is basically the acceleration of the transformation of the accelerations. Let's say it like this. Difficulty. Let's say transformation of accelerations. Okay. I need to find the relative acceleration. So I think instead of this, let me use the pulley as my reference instead of the ceiling, because the pulley and the ceiling are basically, they are moving together. We know that. So as a result, they have the same acceleration, but somehow I can use this. Is the tension of the rope same in both frames? Yeah, the force is not relative, all right? It's not, the value of the force is not going to change between frames and frames. So that's basically a property of the atoms within the string. So this is the force applied by the atoms of the string to each other. They don't change from frame to frame. Okay. So that's an important observation, of course. So what is relative and what is not? So in this case, the relative quantities are like the position, velocity, acceleration, and things like that. These are relative. So when you change to a different reference frame, they change. So these are basically kinematic quantities, but the force doesn't change. Later, we will see that the energies and relative quantity as well, work, energy, and things like that. These are also relative because, yeah, when time comes, we'll talk about this. So let me start with this one, okay? So in any case, so I'll just do the solution in here. So that's basically in accelerated frame. Okay. So that's, I'll be basically starting from the same thing. So as a result, we will have these things in here. So let me use a pink color. Is this pink? So let me call this as acceleration A. So therefore, the acceleration of this one is A in the downward direction. So we are going to solve the problems in the same way. So on M1, there's a tension force applied, pulling it upward, weight force applied, pulling it downward. For this one, tension pulls it upward, the weight is pulling it downward. Do I know that this A is positive? Well, I know that in that case, M2 is heavier than this one. So I know that this is going to accelerate downward and that will accelerate up. So as a result, I know that A will be positive. In any case, I made my first mistake. So instead of gravity in here, I need to write down the total gravity. Sorry, I mean, it's both the fictitious force and the gravitational force, right? It's the real force applied by the Earth plus this imagined fictitious force together. But since both of them have the same form, we just use these the same expression in here. So I'll just solve the problem by treating as if the gravity, the value of gravity has changed, okay? So in any case, the equations are like these. So T minus M1 G tot is equal to M1 times A in here. Let's see, this is M2 G tot minus T is equal to M2A, okay? The trick is to write them down on top of each other and then add them up. When you add them up, these tensions cancel. So as a result, we get like M2 minus M1 G tot in here. And then M1 plus M2 A in here. So we find the acceleration to be equal to the difference of the masses divided by the total mass times G tot. Okay. I mean, let me just quickly do this. So M2, I said that it is 3 kilograms. M1 is 2 kilograms. So it's like these. And the total gravity is 15. So we get like 3 meters per second squared. Okay. So in any case, I'll just draw the picture in here. So again, pulley is at rest, all right? So this is the frame that we are talking about. So this is basically accelerating in the upward direction with an acceleration of 3 meters per second squared. This is accelerating down with an acceleration of 3 meters per second squared. Okay. Now, I would like to basically transform these accelerations to the other reference frame, to the original reference frame. So in that case, I have to look at the relative acceleration relative to this one. And in this case, I have to use a definite reference. I mean, it's going to make the life easier for me if I use a definite reference frame. So in that case, I'm just going to make, I'm just going to remind you that this going down with an acceleration of 3 meters squared, 3 meters per second squared is the same thing as accelerating upward with an acceleration of -3 meters per second squared. These two are the same, okay? Just keep this in mind, okay? So in any case, what I will do is I'm going to choose my y-axis upward. So let's say plus y upward, okay? So in that case, this is the first block and that's the second block. So the acceleration of the first block has a y component which is equal to +3 meters per second squared. And the second block has an acceleration whose y component is equal to -3 meters per second squared. Just a moment. Why did you say 5? Did I make a mistake in here? 3 minus 2. So that part is 1/5. Yeah, no, the acceleration is 3. Okay. So in any case, why did I do this? Because I know that the pulley in the original reference frame has an acceleration which is given by, I mean, these are relative accelerations basically. So let's just remember that that's the acceleration of one relative to the pulley and its y component. There are too many commas in here. I mean, this is the y component of that acceleration. And that's the y component of the other acceleration, okay? The reason why I did want to use the y component is that, I mean, I want to use the same formula. As a result, I actually wanted to express all three accelerations by using the same reference frame, okay? So in any case, so I know that therefore, A1 minus AP would be +3. So A2 minus AP would be -3 meters per second squared. Here, the acceleration of the pulley is the same thing as the acceleration of the ceiling. So that's +5 meters per second squared. So all of these are y components. All right. So that means from here, therefore, so A1 is equal to +8 meters per second squared. And A2 is equal to +2 meters per second squared, right? So let me just say in here, I didn't write this thing down, so note, right? A1, A2, AP, AC, A12, sorry, A1P, A1, A2P are all y components of the corresponding vectors. Right, let's just say it like this. So I'm using a definite y-axis in there. The elevator accelerates upward, right? Not the direction of velocity, but the direction of the acceleration. Okay, so why didn't I write down this y in here? I could have written it like this. I didn't do it like that because yeah, it would be very confusing. So in any case, so that's not really A1. So that's, let's say that these two are, these are also relative to pulley. Because I didn't use the standard convention in here, like writing the relative velocities like that, because that would make the notation complicated. In any case, so these two are relative to ground, or I don't know, let's say relative to an inertial frame. It doesn't matter which inertial frame it is. Accelerations will have the same value in all inertial frames. Okay, I don't know if you have any questions in here. So that's the answer to the original problem, because the original problem is basically asked in this inertia reference frame, and they are asking for the values of these accelerations in the inertia reference frame. And these are the answers to that question. Okay, let's solve the problem in the other frame, right? I'm just going to do it like that, okay? So this is this solution of the same problem in the inertia reference frame. So I don't want to pass to the other frame, but the difficulty in here is that there is a constraint in here between A1 and A2. But since the pulley is accelerating, it's difficult to express this constraint. Okay, so that's the difficulty. That's the one that I would like to solve. You can do it in many different ways. I don't know. Let's just do it like this. So again, the y-axis is upward. So what I want to do is like, I mean, call that distance as like D1 and that distance as D2, for example. So the constraint relationship is that the sum of these two is constant. Okay. I mean, plus that distance is equal to the total string distance. But I mean, since that distance is also constant, it's not going to change this. So since I'm going to take the derivative of that expression, this constant also disappears. So we don't care about these. So what is that distance D1? D1 is basically the position of the pulley. So let's just call this as like the position of the pulley minus the position of the first block. So as a result, for D1, I'm going to write position of the pulley minus the position of first block. For the second distance in here, I'm going to write again position of the pulley minus the position of the second block. So that's constant. Okay. So as a result, what I do is I just take the time derivative of both sides. Okay. So on the left, I'm going to get velocity of P minus the velocity of 1 plus velocity of P minus the velocity of 2. That's equal to 0. So that's a constraint relationship between velocities. And then I take the time derivative of both sides again. And the right-hand side is still 0. In that case, we get AP minus V1 plus AP minus, A1 minus AP minus A2, that's equal to 0. Or we can say that, let me use a white color now. A1 plus A2 is equal to 2AP, which is basically 10 meters per second squared, right? Acceleration of the pulley is given in the problem. So somehow that's the constraint relationship in here. So it basically says that the sum of these two accelerations should be fixed. And fixed at this particular value. So as a result, we know what the constraint is. Okay, let me separate these. Okay, so in that picture, therefore, that's the thing that I should be using. So I know that if the pulley is not, for the case when the pulley was not accelerating, that's the correct relationship. So in that case, the right-hand side would be 0. A1 plus A2 would be 0. So that means these two accelerations are equal in magnitude, but opposite in directions. Okay, so therefore there is a way to check them actually. Right, there's another way of deriving this, or we can do it like that. So we can basically pass to that accelerated reference frame for a moment, at least for deducing the constraint relation. So let's say it like this: in the frame of pulley. Okay, so this is at rest. This has an acceleration upward, which is basically the relative acceleration of 1 relative to pulley. This has an acceleration, relative acceleration, which is A2P. Okay, So I know that this is at rest. So as a result, in that case, these two accelerations are equal and opposite. So as a result, I would say that, so A2P numerically should be the negative of A1P. Okay, I had to use the same direction because this is essentially the y-axis. So that's the correct way of expressing it. I didn't want to do it in the opposite way. In any case, so as a result, we have A2 minus AP is equal to minus A1 minus AP. So by just arranging the terms, we then get this result, which is the same result again. Okay. That's kind of easier because you don't have to take derivatives. But again, I mean, you have to use some kind of a relative thing. I think this is one of the homework problems, right? There are some comments, but I'm not reading the comments. Why did we took derivatives to find acceleration? Because, I mean, I'm interested in the accelerations because I'm going to use them in the Newton's second law. So as a result, I would like to find the constraint relationship between the acceleration. So that's my final aim. But here I started with the distances in here, positions, because it is easier to express the constraint in here in terms of the positions, because the constraint is the fact that the string has a fixed length. The length of the string doesn't change, all right? That's basically the constraint in here. So as a result, by using the positions, I can express this clearly, but from here, eventually I need to reach to the relationship between the accelerations. Okay, so in any case, so that's the important step in here. Sorry about this, I'm going to move it to the right side. So as a result, that's what I'm going to do then. I'm going to draw the free body diagrams. Okay, so on this one, the tension is pulling it upward. There is no fictitious gravity or anything. That's just a real gravity. So in here too, the tension is upward and the weight is downward. And I know that this has an acceleration of A1 in the upward direction, A1. That has an acceleration of A2 in the upward direction. What else? And then we have this relationship in here. Okay. So let's then write this thing down. So that's T minus M1G, that's equal to M1A1. So that's Newton's second law for this one. Newton's second law for this one is T minus M2G is M2A2, okay? And then we have this, so we have these three equations. Okay. I think what I'm going to do is I'm just going to add 1 and 2, because in that case, I can cancel the tensions in here, okay? So they will cancel. In any case, we get M2 minus M1G here. And on the right-hand side, I'm going to get M1A1 plus M2A2. And then I'm going to replace this by the third equation. So I'm going to write this thing down as like 2AP minus A1. Okay.
Why we add them? Should
Because
we subtract
them? Yeah.
Subtract, yeah.
Sorry about that. Yeah, there's a minus sign in here. Thank you very much. Yeah, it was, okay. So let me also change this, so subtract them, okay? Thank you very much for the warning. Otherwise, we would be in deep trouble. So messes were like 3 and 2. Gravity is 10. Mess 1 is 2, so that's 2A1. Mess 2 is 3, so whatever. So that's 10. And then we have A1 in here, which means on the right-hand side, I get like 5A1 minus 30. On the left-hand side, I get 10. So A1 is equal to 40 divided by 5. So that's 8 meters per second squared. So which then implies that A2 is equal to 2AP minus A1. So that's equal to 2 meters per second squared. Okay. So we got the same results. But here, I didn't have to change to pass to an accelerated reference frame, perhaps for deriving the constraint relationship. But in any case, I think, yeah, this was the same answer in here. So in any case, so let me quickly compute T. So once I find this, right, I can use the first relationship. So that's T minus M1G. That's equal to M1A1. So the tension is T, M1 is 2, gravity is 10, that's 2, and the acceleration is 8. So that's 16. So the tension is 36 newtons. And T prime is 72 newtons. Why did I compute these? Yeah, I think. Okay. So in any case, so yeah, all right. Okay. So in any case, let's just put it like that. Okay. All right. This is my system in here. So in a way, I'm pulling this system upward with a force of 72 newtons. Okay. So what I can do is I can consider this whole thing as a system, right? This is a system with a mass, let's say, which is the total mass, which is basically M1 plus M2. The pulley is massless, so as a result, this is 5 kilograms. Okay. So apparently, therefore, the total weight in here is equal to, what is it? The total mass times gravity. So that's 50 kilograms. So in any case, so this tension in here is basically applying an upward force on the system, which is bigger than the total weight. And the question is, what does it mean? Can I use this information to deduce something? Yeah, I don't know. I mean, I cannot find any relationship whatsoever, all right? Let me just say this. The problem in here is that this is a system where within the system, the blocks are moving relative to each other, right? They are actually accelerating relative to each other. So as a result, in that case, I cannot really say anything about the total external force applied on the system and the acceleration of the system, because I cannot define a single acceleration for the whole system, okay? So that's perhaps the most important thing in here. So note, we cannot define a single acceleration for this system. And as a result, I cannot really use these values to deduce something in here. Later, the reason is that this first block has a different acceleration than the second block in here. So these two values are different. And so as a result, it is quite difficult to find a common acceleration value. But later, a few chapters later, we are going to see that there's a very special point in here, which is called the central mass. And I can really relate these external forces to the acceleration of the central mass later, okay? But here right now, we cannot use this information. Okay, let me talk about the same thing in here, okay? So I'm not going to solve the same problem of finding the tensions in here. Let me just add that the tensions are the same in here. So that's the ceiling reference frame. Okay, so the ceiling is at rest, the pulley is at rest. Okay, here the gravity is the total gravity, which is 15 meters per second squared. Okay, so in that case, the apparent weight in here is going to be the total mass times the total gravity, which is like 5 times 15, so that's like 75 newtons. However, the tension in here is like 72 newtons. And the question is, why is this value different than this value? You might ask the question like, why they should be the same? That's indeed a very good question. Well, I mean, normally you would expect them to be different from each other. So, I mean, normally, if somehow I stop by nailing this, I don't know, this pulley in here, so that I stopped this string from going around the pulley. So the pulley is fixed in its position. So as a result, these two blocks are not accelerating. In that case, the tension in that upper string will be equal to the total weight, which is basically 75 newtons in here. But once I remove that, that nail in here, and then the pulley starts rotating, in which case these are going to accelerate up and down. In that case, the tension in the upper part of the string becomes smaller. Okay, so there is some kind of an explanation for that. But when we see the central mass concept, perhaps it is kind of easier to explain this. Okay, so I'll do that later if I remember this argument. But I just want to mention this in here. I didn't want to confuse you. So if you are confused about this, then just forget about this. Okay. Okay, so I don't know if you have any questions. This is actually one of the simpler questions that can be solved by these methods actually. Now I'm just going to actually discuss something about the effect of Earth's rotation. So let me take your 4 more minutes. Right. Since Earth is rotating, the ground is not an inertial reference frame. Right? We are in an accelerated reference frame. So relative to us, it looks like nothing is moving, but we are actually accelerating, all right? So as a result, we have to somehow take this into account and make a correction. So as a result, how can we correct this? I mean, let's say it like this. If we had to use the ground as our, as our reference frame, okay, then how can we correct this? So let me put the question mark in here, okay? If we have to use the ground as our reference frame, then we have to do some correction in here. Well, how can we correct this? Well, we basically, let's say it like this. So the answer is obvious. by adding the fictitious force or by adding the fictitious gravity, which is what I'm going to do, okay? But let me add one more thing in here. So let's say it like this. So this is the Earth, right? This is the Earth. There are these kinds of motions in here. So first of all, it rotates around itself. So there's a rotation motion, rotation around itself. We just call this as the spinning motion. Okay. I mean, the spin is the motion that an object has around itself. Okay. So, but it also rotates around the, I mean, it's on an orbit around the sun. So there's also sun in here. We will talk about this orbit later when we talk about gravity. So it also does a motion around the sun. And as a result of that, Earth is also doing this accelerated motion. Okay, so as a result, if we are on the Earth, then we will be basically following a very complicated path, right? We will be moving like that. Probably we won't be coming back. Sorry about that. So we will be following some kind of a wobbly path in here. That's not the only motion. We also know that the sun is also rotating around the center of our galaxy, right? There's a huge, so that's the center of galaxy. Okay, so the sun is also doing this circular motion in some certain orbit. So as a result, we, together with the sun, we also do this. So as a result, our real orbit is actually much more complicated than this. Okay, so in any case, what we do is like a complicated accelerated motion in space relative to some inertial reference frame. And we would like to find out the effect of the fact that we are using an accelerated reference frame on our equations of motion, right? We have to find them. Okay, so I'll just tell you this. The effect of the sun rotating around the galaxy and the effect of the Earth rotating around the sun, these are actually quite small, much smaller than the effect of the Earth spinning around itself. Okay, so as a result, within that problem, I'm just going to handle this one, okay? So I'm just telling you this, but you can also do the computation. I'm just going to compute the effect of that one. So the first thing, this is the first. The second one is that, well, this is actually a rotating reference frame, right? It's not just the, I mean, when I started about the discussion about the reference frames, I said that, well, let's assume that the X and the Y axes are pointing in the same direction. Okay. Assume that these are not rotating, right? But here we basically have a rotating reference frame. Why? I'm just going to draw the picture like that. So suppose that this is the Earth. So that's the north, and that's the equator, right? And we are somewhere in here. So we will be choosing our y-axis. I mean, the Turks are in here, right? Somewhere in here, right? So in any case, we will be choosing the y-axis pointing upward. Let's say that x-axis is like that. And so therefore the z-axis will be pointing like this. Because this has to be a right-handed frame. So when we go around the this axis of the Earth, this directions also change. So therefore, this is a rotating reference frame. It's not just accelerating; it is rotating. Right? The rotating reference frames are even more difficult than the types of reference frame, the accelerated motion than that we are thinking in here. So as a result, these are a little bit more complicated. So as a result, let's just forget about these, okay? But I'm just going to compute the acceleration in here. Okay, what we need to do is like, I need to compute my acceleration or acceleration of the ground in here because of the spinning motion of the Earth. and then we will look at the corrections. Okay. Let's first of all do the calculation like this. So this is the Earth. I'm just going to first, this is the North Pole, that's the South Pole. So let's say that this is the equator. So I'm going to compute the acceleration, acceleration of ground, let's say, for a point on the equator. Okay. So the first question is, this is a relative motion question. In which direction does the Earth move in this rotational motion? Does it move towards east or does it move towards west? To east or to west? Somebody said east, but I'm not going to give any answers in here. Just think about this thing. So, I don't know, this is one of the fun things to think about. Later, I'll give you the rule. In the second hour, I'll give you the rule in here. It's a very simple rule, actually. So let's stop here.